All right, it's Tuesday, February 16th, 2021, Physics CP. I'm going to try to go over two main concepts for now. One of them being centripetal force calculations, which technically we've already covered. And the second one is called Newton's law, universal law of gravity. Universal law of gravity, U-log. And so let's see how we do on that. So to start off with, the first part is I have a circle. And the circle has a radius of r. And I'm traveling at a speed v as I go around the circle. And not that we need to know it right now, but I have mass m at the end of the string or whatever it is that's making me go around the circle. This is a situation that we call uniform circular motion. And what does that mean, uniform circular motion? That means constant speed and radius. So it's a circle, and you're going around the circle at a constant speed. Earlier in this course, I had inflicted on you the formula for calculating centripetal acceleration. That's what it's called. The name centripetal means center seeking. If I have a mass on a string and I twirl it around in a circle, if I let go of the string, the mass will go flying off at a tangent. Whenever the string is broken. So if I break it at this moment, I go off at a tangent. If I break it when it's up here, it would go off at a tangent. If I break it here, it would go off at a tangent. So what keeps it from going off at a tangent is called centripetal force, and the change in direction is called centripetal acceleration. I never did derive the formula for you, but here it is. Again, as a punchline, centripetal acceleration is your speed squared divided by r, the radius. As an example, okay, so per student request, we any two variables we can solve for the third. If I knew v and r, I can solve for a. If I knew a and v, I can solve for r. If I know a and r, I can solve for v. So making up a problem, suppose that the speed is 14 meters per second. And so either I now need to be given the acceleration so we can solve for r, or I need to be given the radius so that we can solve for the acceleration. All right, student is randomly selected. Let's set the radius to be 9.0 meters. Keeping in mind, if the units were centimeters, you'd have to convert them to meters for our calculation, or be careful, right? So given v and given r, solve for a. That would be equal to v squared divided by r. That would be 14 meters per second quantity squared divided by 9 meters. And this is why we use calculators. 14 squared divided by 9 is Yikes. So you can see the answer now. 14 meters per second squared divided by 9.0 meters. Notice the units. Meters per second squared is meters squared per second squared. When you divide meters squared by second squared by meters, one of those meters will cancel, and our answer will be in units of meters per second squared, which is an acceleration. And 14 squared divided by 9 rounds off to 22 to 2 sig figs. So the centripetal acceleration in this first example was 22 meters per second squared. Let's practice some more and do a second example. In the second example, instead of being given the speed and the radius, let's be given the acceleration and the speed. All right, random student value, an acceleration of 23 meters per second squared. Now we need a random value for the speed. Random speed is 18 meters per second. Calculate, please, what would be the matching radius for this example. The formula, of course, is centripetal acceleration is equal to v squared divided by r, but this time we need to rearrange the equation to solve for r. I could do that in 2 steps by multiplying both sides by r, and then dividing both sides by the acceleration. Now that you've rearranged this one formula to solve for that one unknown, calculate, please, if the centripetal acceleration is 23 meters per second squared and the speed is 18 meters per second. I see you have a typo here, 18 meters per second. Calculate, please, what is the corresponding radius? Okay, this one went well. The students have calculated the corresponding radius would be 14 meters. Notice that the units will always work out correctly. A speed squared is meters squared per second squared. And when I divide that by meters per second squared, one of the meters will cancel and both of the seconds squareds will cancel, or the second squareds will cancel. And sure enough, our answer will be strictly in units of meters. Throughout this course, the units will always work out correctly. I'm still skeptical that maybe we need a third example. So we had given V given R, then not vegan. Then we had given A and given V. So now how about given A and given R? Let's see if we can take that one far. All right, so we're going to set our acceleration to be 10 meters per second squared. All right, our random value for the acceleration is 10.0 meters per second squared. Our random value for the radius is 8.0 meters. And this time, you need to rearrange the equation on your own to solve for the corresponding speed. Calculate, please, what is the matching uniform circular speed. Okay, so this time you had to rearrange for v, which meant taking the square root of r times the centripetal acceleration. And the students worked out it is 8.9 meters per second. Great. Well, it's occurred to me I can give you one more example. Yes, because at one point in teaching about centripetal acceleration, I had taught you that when you have a circle of radius r, you can complete the circumference 2 pi r in a period of time, capital T, which means your speed v is that distance you travel, 2 pi r, divided by t, the time it takes to go around the circle once. And substituting this value for v into the centripetal acceleration equation, we have centripetal acceleration is equal to 4 pi squared times r divided by t squared. So let's do one final example, a review problem. My three variables are acceleration, radius, and period. So this time, let's do acceleration and period and solve for radius. Our random acceleration is 16 meters per second squared. Our random period is 7.50 seconds of time. Rearrange and calculate, please, what is the corresponding circular radius. Okay, well, this one certainly is a struggle for the students. We have to rearrange this equation to solve for r. And r, in this situation, when we rearrange it, is going to be equal to the centripetal acceleration times the square of the period divided by 4 divided by pi squared. Plugging in the values, 16 meters per second squared for the centripetal acceleration, 7.5 seconds for the period, squaring that, dividing everything by 4, dividing everything by pi squared, I get a value of 22.8 meters. I did have one student get that result and plenty of others who did not get that result. All right, well, so much for that review. It said centripetal acceleration is equal to v squared divided by r, or 4 pi squared r divided by t squared. The other review that we're trying to do is to calculate the centripetal force. The centripetal force is mass times the centripetal acceleration. So, for example, if I have a mass that is given and any of those other variables given that we were just working on, our choices are the radius, the speed, the period, or the acceleration. And they're grouped, right? So acceleration, radius, and speed, or acceleration, radius, and period. Add to that mass, and we can calculate centripetal force. So let's randomly say, suppose I have the speed. See, what we don't want is to say that we have the speed and the period. That just isn't what we're set up to do. So either acceleration and speed, or acceleration and radius, or acceleration and period, or dot dot dot, or dot dot dot, or dot dot dot, but not dot 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 dot. Got it? Great. So I guess I'll just make up something radius and period. Calculate the centripetal force. All right, we need some numbers. For random mass, we're going to use 6.00 kilograms. For random radius, we're going to use 10.0 meters. For random period, we're going to use 4.70 seconds. Based on these givens, calculate, please, what is the centripetal force needed to keep this 6 kilogram mass in a circle of radius 10 meters with a period of 4.7 seconds. Calculate, please. All right, excellent job, students. Solving for the centripetal force, it's going to be the mass of 6 kilograms times the centripetal acceleration. Enough information is given that you would go m4 pi squared r over t squared. Beep, beep, beep. The result was 107 newtons. Ta-da! So this period, I've reviewed with you students centripetal acceleration and centripetal force. Of course, this being another variable, we can have to rearrange and solve for other unknowns if the centripetal force becomes the given. So if the force is given and the mass is given, you could solve for the acceleration. Or if the force and acceleration are given, you solve for the mass. Same story for all of class. The second topic that I wanted to cover this period was called Universal Law of Gravitation. This was developed by Isaac Newton, and I'm a little pressed for time, so I'm not sure if I should give you the background on this formula. Okay, so once upon a time, there was this high school graduate who got accepted into college, and he got all set to go off to college, but the pandemic broke out and he had to stay home. While he was home, he invented calculus and solved many of the mysteries of the universe. This happened back in the 1600s. This kid was Isaac Newton, and he worked out amazing concepts before he even entered college. Yikes. So here's one concept I'm going to try to share with you. The story is that once upon a time, there was an apple tree, and the urban legend was that the apple fell and it hit Isaac Newton in the head. We don't think so. I don't think so. I grew up on a farm that had 2 apple orchards. And so after school, it was always fun to just walk around and pick an apple off the tree and eat it. And yes, on occasion, I could hear ripe apples falling to the ground somewhere in the orchard. And I believe that's what Isaac Newton had occurred to him, that he heard an apple falling somewhere in his apple orchard. At the same time, you might notice that this evening, if the sky were clear, you go out in the west, and even before sunset, you can see the moon up in the sky. Isaac Newton wondered to himself, if the same invisible force that caused the apple to fall to the earth could be the same invisible force that he believed was making the moon accelerate towards the earth. Now, why did he think the moon was accelerating towards the earth? because he's the guy who worked out this whole formula dealing with centripetal acceleration in the first place. He's the one who said, oh, it would go off in a straight line if it wasn't being pulled towards the center. Pulled towards the center. Pulled towards the center. Centripetal acceleration. So he imagined if this is the Earth and this is the moon, then there must be some invisible force accelerating the moon towards the Earth. He speculated it was the same invisible force that would make an apple fall out of a tree. Brilliant insight. So he went about trying to develop a formula to express this property of nature. And one way that I can try to get you to imagine how he came up with one part of his formula is to talk about a candle. Imagine that this is a candle. There's a candlestick, and it's shining away nice and bright. I surround the candle with a sphere that is exactly 1 meter in radius. And I line the sphere with all kinds of photodetectors. These photodetectors collect all the light being emitted by that candle. And let's say I turn that into energy and say, oh, this candle is shining with an energy of 1 joule in every direction per second. 1 joule per second. So that's a power measurement. But let's say it's energy of 1 joule every second of time. That's how much the candle shines. If I were to remove this sphere and replace it with a sphere twice as big in radius, I've been asking my aerospace students, how do they think the energy would compare? I've been asking my AP Physics students, how do you think the energy would compare? And mathematically, I can tell you the formula for the surface area of a sphere is given by 4 pi r squared. So if the first sphere has a radius of 1 meter, the second sphere, if it has a radius of 2 meters, the second sphere would be 4 times the surface area of the first sphere. Now, does that even matter as far as my question goes? My question was, if I replace the first small sphere with a second twice as big sphere, how much energy would the second sphere measure if I completely filled its entire surface with photodetectors? Interestingly enough, my physics CP students, like the students in my advanced courses, are not really coming up with the right guess. The correct answer is the total energy being put out by that candle is the same amount no matter what the radius is of the sphere that's collecting all of that energy. Whether I have a small sphere or a medium sphere or a huge sphere, the total energy being put out by that candle is still, let's say, just 1 joule of total energy each second of time. What does change is the intensity of that energy. It spreads out over greater and greater surface as the radius increases. The intensity, the brightness per square, whatever, centimeter meter, whatever unit you want to pick, is going to be 1/4 the intensity that it was on the smaller sphere, because the surface area is 4 times as great. And more generally, the intensity, if I can use a badly drawn math symbol for is proportional to, will vary as the square of the radius, the square of the distance from the center of that candle. If I double the distance, the brightness or intensity per unit area is 1/4. Triple the distance, 1/9. Quadruple the distance, 1/16, and so forth. Isaac Newton, to his credit, said, okay, I'm on the earth. I just saw this apple fall or heard it, and I know that it's not significantly above the earth. Maybe it fell from 2 or 3 meters up, but the earth is 6,378,000 meters in radius. So essentially, the apple is on the radius of the earth. He knew the radius of the earth. Remember, Columbus proved the world was round in 1492. Here's Isaac Newton in the 1600s into 1700s. So yes, they had a value for the radius of the earth. He knew the acceleration due to gravity value, almost 10 meters per second squared. He worked in English units. I don't even know if the meter stick was invented when he did his work. He knew the radius of the earth. He knew the acceleration due to gravity. Thanks to Copernicus from the 1570s, he knew the radius of the moon's orbit around the earth. And he knew the amount of time it takes for the moon to go around the earth once. That is called one lunar month. Right now we're in Lunar New Year. So he was able to calculate the acceleration of the moon towards the earth, the centripetal acceleration. He had enough information. Remember, you don't need the mass for the centripetal acceleration. You just need the other pieces of information. And he predicted what the acceleration would be of the moon if his formula were correct. And his formula predicted that the acceleration due to Earth's gravity would fall off as 1 over the radius squared of the distance from the center of the Earth to the center of the moon. His prediction matched his calculation. This was exciting. This means Isaac Newton worked out a formula to calculate the force of gravitational attraction between any two masses in the universe. That is called the universal law of gravity. And the formula is, the force of gravity is, and I'll be formal for now and put in the minus sign, which means, like our study of static electricity, it is always going to be an attractive force, is the product of a constant times one mass times the second mass divided by the distance from the center of one to the center of the second squared. In physics CP, we dealt with Coulomb's law, which said the force of electrical attraction between any two charges is lowercase constant, Boltzmann's constant K, times charge Q1 times charge Q2 divided by the distance from the center of one charge to the center of the other charge squared. This is for electrical force. This is for gravitational force. The equations are very similar to each other because Mother Nature behaves in the same kind of way where forces and intensities generally fall off as the square of the distance. For the gravitational force, capital G has a value of 6.672 times 10 to the negative 11th power newtons meters squared per kilogram squared. It is the least well-known constant in physics because it's very hard to measure the mass of the Earth precisely. Let's do an example. For example, mass 1 has a value of 10 kilograms. Mass 2 has a value of 15 kilograms. And the distance from the center of one mass to the center of the second mass, a distance of 5 meters. All right, so plugging all of that in to calculate the force of gravitational attraction between them, the minus sign is always there, only meaning gravity always attracts. There is no anti-gravity that repels the way there is repulsion in electricity. There's only attraction between matter and the universe. Even antimatter has positive attraction. There is such a thing as antimatter. So you're going to be plugging in 6.672 times 10 to the negative 11th power newtons meters squared per kilogram squared times mass 1, which is 10 kilograms, times mass 2, which is 15 kilograms. Divide all of that by 5 meters, quantity squared. Beep, beep, beep. Calculate, please. All right, so the students calculated that this is an attractive force of negative 4.00 times 10 to the negative 10th power newtons. This is incredibly weak on the scale that we're used to dealing with. I have a bowling ball and a much more massive bowling ball. They're separated by half the width of a classroom, and the force of gravity between them is 10 to the negative 10th power. That is teeny, teeny, tiny, tiny. The one thing about gravity is, as weak as it is always attractive. So all matter in the universe attracts all other matter throughout the universe. You are attracting the stars to you right now. The stars are attracting you to the stars. The sun is attracting you to the sun. You're attracting the sun to you. The moon is attracting you to the moon. You're attracting the moon to you. Everything in the universe is pulling on everything else in the universe that is made of matter.